we can mitigate the impacts of floods, right? Flood hazard reduction. What sorts of tactics can we use? Well, the first thing that you really should do is identify the area at risk, right? You want to make sure that you know which areas are at risk of flooding. And that's what's being done here. They've actually looked at the, let me make sure I got this right. It's the 100 and 500 year floodplains, I think. So they mapped those out, 100 and 500 year floodplains, and then mapped out which properties are touching those floodplains. And so what you'd be able to do then is be like, you own this property, you are on part of the floodplain, be aware that that risk is there. So we identify the areas at risk. Now, this is another website, and this is Harris County, but if you live in Montgomery County, they have a similar one. It's a map, an interactive map that you can go to. You can figure out where your house is and find out how close you are to a floodplain. All right, so once we identify that area at risk, one of the things you can do is have restrictive zoning. And this is where you would zone an area that you can't build any buildings there because it's in the floodplain, right? You can't have any housing developments. You can't have any businesses or stuff like that. You would zone it just for maybe parks or parking lot or pasture land, something that if it gets underwater, it doesn't cause a lot of damage. It's relatively unpopular in certain places because for whatever reason, people don't like being told not to do stupid things. It's a good way of preventing flood damages, but a lot of people don't like it. It's like I said, don't like being told what to do. All right, another tactic, and this is something you'll see around here used quite a bit, these retention zones. What these are, they're these lower areas. Notice how this is lower than the neighborhood that's back there. And also notice that it's all grass and soil. It's something permeable. So what the idea with this retention zone is, it's in an event where that neighborhood would flood, all the water from the neighborhood is actually sent to this area where it can sit there and it can soak into the ground and not flood the neighborhood. And fine, you know, the kids can't play baseball or football or stuff for a little while, but at least their house isn't flooded. These do work up to a point, right? There is a limited volume these can hold. Now, I did not live here back when Tropical Storm Allison hit, but I am told that that neighborhood flooded even though they had the retention zone, mainly because so much rain fell, it filled up the retention zone and then it flowed into the neighborhood anyway. So effective, but do realize that it's not perfect. And there you can see one of these doing its job, holding water out of the neighborhood. Now another thing that's done is you can have diversion channels. Well, if you divert something, that means you send it somewhere else. These diversion channels will take the waters that would flood a neighborhood and sends it to a place where it hopefully will be not causing damage. This is what some of the diversion channels look like dry, right? And there's the same one doing its job. There's one near my house, and there it is doing its job. Well, where do these diversion channels send all that water? Typically, it's to a flood control dam. Now, flood control dam is a little bit different than other dams. You know, if you live up in Conroe, you know, you have Lake Conroe there. Well, Lake Conroe, they actually try to keep full for the most part, as filled as possible, because they use that lake to generate electricity and as a source of water for irrigation and all kinds of other things. Well, a flood control dam is kept as empty as possible, right? They don't want any water behind the dam, because what happens in a flood event, those diversion channels carry all that water to this empty space, right, behind the flood control dam, and the flood control dam holds that water that would otherwise be flooding neighborhoods, And what they do is they will slowly, the operators of this, usually the Army Corps of Engineers, will slowly let water drain from the dam in a safe volume that's not going to be flooding any places. I live out in Cypress area. South of me, there's a couple of these flood control dams. It's what, Addicks, I think it's Addicks. And it was built, I think it was in the 1940s, to hold floodwaters that would otherwise be flooding Houston. And so these things do exist in this part of the world. One bad thing about flood control dams, and actually dams in general, is they can get silted up. This is a dam, and there's supposed to be a big body of water behind it. That's all now sediment. And this can happen with flood control dams as well, because what occurs is the water comes in there and it's moving, right? And I told you guys, when water is moving, it has a lot of energy, it can pick up a lot of sediment. Well, if it's a dam, right, now we've created an artificial lake, that standing water, low energy, all that sediment is going to get dropped off. So over time, the volume that those flood control dams, the volume of water they can hold decreases because you have this addition of sediment behind the dam, which we call the silting of a dam. And you either have to be aware of that, or you have to you have to dredge that area out, get rid of that silt to make sure you can still hold that volume of water. All right, common thing people hear about when it comes to flood control are levees. Well, levees are a raised bank of earth, or sometimes they're concrete, but it's this like artificial hill, and the river is on that side, and the idea is if the river rises, this is going to hold the water on that side and not flood all of the land on this side, right? It's just basically this artificial hill holding back the river water. The bad news about levees is they break. And no, you don't need to memorize all of the ways they break, but I did want to point out there are a lot of ways levees break. So when there's news that there's a flood on the Mississippi and levees have broken, it's like, yeah, that happens in every major flood, levees break. So just be aware that they can be effective, again, up to a point. Sometimes you get the river rising higher than the levee. Sometimes the levee just collapses and breaks and the water flows past it anyway. They're not perfect. So don't move to a place and think to yourself, there's a levee, I'm perfectly safe. Well, it offers some safety, but it's definitely not perfect. Now, similar to a levee are flood control walls. This is basically a big wall. It has a watertight door. Now, when there's not a flood, you have that door open, and so we have the river and we have the wall here, and we're on the protected side. If a flood is coming, you'll close that door. See, there's the town, there's the wall, and here's our big door. They would close that door to hold the water on this side of that flood control wall and hopefully protect that town that's behind it. Do want to point one thing out here. This wall did not exist in the Great Flood of 1993, but it wouldn't have done anything if it did, because those houses, see that hill there? So we're looking at the edge of one of the floodplains. Those houses were underwater in the Great Flood of 93. And that's how high the water got. And so again, these are very much like levees. They are effective up to a point. If the floodwaters rise higher than this, wall's not going to do anything. The wall can potentially break as well. So again, effective, not perfect. All right, what about forecasting floods? Come on, we live in the Houston area. Everyone's seen, like, there is a flood warning or a flood watch, right? And this is something that happens, sometimes it seems, on almost a daily basis here. Well, this is a partnership between the United States Geological Survey and the National Weather Service. So what the USGS does, they have all those stream flow gauges, right? They have the real time, they know how much volume of water is flowing in the stream, they know the rock type and the soil type, so how much infiltration can be expected and so on. The National Weather Service knows the precipitation history and the precipitation forecast, so they know how much more water is going to be added to that. And so what these guys do then is they take all that information and they construct a projected hydrograph. So you're kind of like, well, this is what's happened so far, this is what we think is going to happen in the future. This is how high we think the floodwaters will get, and this is when we think the crest of the flood will arrive. And these are actually fairly accurate. I know with a number of my lectures, I'm like, we don't know what we're doing. Okay, not quite that bad. Volcanoes we're pretty good at too, but earthquakes, we don't know what we're doing, you know, sorry. We try to know, but these are one of the things kind of like volcanic eruption forecasts. We're pretty good at that. We're pretty good at forecasting how high and when the crest of the flood is going to arrive. Of course, though, come on, this is my like death and destruction class. I can't be perfectly like happy. We're good at this. I do have to point out there is some bad news. The bad news is less streams are being monitored every year. And this is a graph showing the number of stations, so the number of stream flow stations with 30 or more years of record that are discontinued every year. And more, they just don't monitor the stream. They just don't update the gauges and don't monitor them anymore. You might be sitting there like, why won't they do that? Well, that does cost money, right? You know, this is not for free. This is what your taxes go to. If you don't fund that, it can't be monitored. Geologists don't work for free. So unfortunately, it could potentially get harder to do this if we don't have good data to forecast those things. All right, let's take a quick look at an example of an upstream flood, a flash flood, and an example of a downstream flood, a long-term flood. And we're going to go to Big Thompson Canyon in Colorado in 1976. And in the afternoon or evening, strong low-level winds were blowing from the east. Now, here's what was going on. And this is what happens at the Front Range. So the Front Range is where the Great Plains and the Rocky Mountains meet. And typically in this part of Colorado, what occurs is you have these low-level winds that are blowing from the east. They hit the Rocky Mountains, and the wind is forced, the air is forced to rise. Remember that rule I said about when air rises, it cools. And when air cools, it can't hold its water anymore, its humidity anymore. And so you start getting rain. Now, normally, you have upper level winds that are strong and they're blowing to the east. So what usually happens there in Colorado is this rainstorm builds up here, but then these winds push it out over the Great Plains. What happened back in 1976, these upper level winds were not blowing. These upper level winds weren't blowing, so this rainstorm sat there instead of moving out over the plains, just sat there. So what ended up happening is rain began to fall, and in fact flood warnings were called, and people were told to evacuate this canyon, but because it often rained in the afternoon and usually nothing happened, a lot of people didn't listen to that. And so 12 inches of rain fell. That's in this one area, and that's more than a year's worth of rain for that part of Colorado. And this flash flood of 6 meters deep, remember a meter is like about this, so 6 meters deep, went through this canyon about 25 to 30 kilometers an hour. You can see it killed a number of people. Many people were never even found and caused a lot of destruction. And this is what it looked like. You can see the road here, and the road just disappears. It would go up that canyon there, but it's completely covered by all of the water in that flash flood. And you can see why this would flood very quickly too. We have steep walls, right? So this water is almost immediately being, the rain that fell is almost immediately going into that stream there at Big Thompson Canyon. There's a house that got stuck on a bridge, that got lifted up by that. Now, just to let you know, this is not an isolated thing. That was 1976 that I showed you there. This is a a hydrograph from 2013. And notice, everything's going on. Boom! Another flash flood, because the same thing happened. You had these this storm build up there, weak upper level winds that would not push the storm away from the mountains onto the Great Plains. So all this water fell over this one little area and caused another major flood in that same canyon. So anyway, that's Big Thompson Canyon flash flood. Let's look at a downstream flood though, and this is the Red River, but it's not the one you're probably thinking of. It's the Red River of the North. It flows between the Dakotas in Minnesota, and it flows northward into Lake Winnipeg in Canada. And the winter of 1996 to 1997, it was really, really snowy. There were 8 major blizzards. One of the blizzards in, I think it was in March, dropped 1 meter of snow over the area, so basically we got a lot of snow there. Now the Red River, like I said, it flows to the north. So what happens, the headwaters thaw first, right? Because as springtime comes, spring sort of slowly moves northward. So the headwaters thawed and water started flowing, but up towards Lake Winnipeg, towards the mouth of the river, it's still frozen. And so you got all these ice dams forming. And so what happened, normally the rivers discharge, and this is at Grand Forks, North Dakota, it's 75 cubic meters per second. You can see in the flood of 1997, 3,400. So just imagine, that's a huge amount of water that ended up flowing. The crest was 8 meters over flood stage, so it was 8 meters above where it starts flooding things. And remember I said these downstream floods can last a long time? This lasted from the 26th of March to the 20th of May. So you've got like 2 months of this flood lasting there. So this is from the Army Corps of Engineers, and what you can look here, there's kind of this little squiggly white line right there. That's the Red River of the North, where its channel is located, and the blue shows you all the areas that are underwater. So again, if we look at the scale down here, this is 10 miles. So for basically 5 miles on either side of the river was flooded. This is on a normal day. There's the river. Same bridge during that flood. This was a weird flood too, because this is a city of Grand Forks, and you can see it's flooded. There's where the river normally flows, is between those 2 trees right there. There's a railway bridge. Notice the smoke. So this was a really weird circumstance where the entire town's flooded, but it started burning down because they started getting electrical fires in those buildings. And that was a major disaster because they couldn't get to the places to put the fires out because everything was flooded. And eventually they brought in some of the wildfire fighting aircraft to try to put the fires out before the entire town burned down. There we are in town, just to show you how high the floodwaters could get. All right, last thing I want to talk about is New Orleans and the Mississippi. So New Orleans was established in 1718 on a natural levee, and so this was a natural area of high ground next to the Mississippi. And the French Quarter is that original old part of New Orleans. And so it is actually the highest area around because the original settlers picked the best place to live in that area. Levees are built to protect the city, but they fail in every major flood. But here's the really bad thing. As the city grew, they started draining swamplands around the city to build things on. And the thing about soil in swampy areas is it's very porous and it can get compacted if you put any kind of weight on top of it. So what ended up happening, they would drain these swamplands, build a bunch of stuff on there, but the weight of all of these structures started compacting the soil, so those neighborhoods are actually subsiding. They're dropping lower and lower. And so many of the neighborhoods are actually below sea level now. And that's one of the reasons why they have major issues with flooding in New Orleans, especially in certain neighborhoods, because those are the ones that are built on those drained swamps that are now well below sea level. Now there's also this thing called the Atchafalaya problem. Remember I mentioned that rivers at their deltas like to move. And pretty much the state of New Orleans, the southern part, or state of New Orleans, state of Louisiana, the southern part of the state is all built on delta deposits of the Mississippi River. All right, so what's this, I hate that river name, Atchafalaya? This is not Norwegian. Okay, the problem with that river, so the Mississippi today is flowing this way. And what we're seeing with each of these little colored lines, it's showing you where the delta was located in the past. So back when the Egyptians were building their pyramids, the river was actually flowing down here, building a delta here. Let's see, around 1100 to 1300, the Middle Ages, the river was flowing here. Today it's flowing here. Well, let's get to this problem. The Mississippi no longer wants to flow this way. It wants to switch its pathway, and it wants to now flow down the Atchafalaya and start building the delta here again. Well, so the U.S. Army Corps of Engineers has been given the task to force the Mississippi River to continue to flow past Baton Rouge and New Orleans. Well, why would they do that? That costs a lot of money to force the river to flow where they want it to flow rather than where nature wants it to flow. Well, it really has to do with business. There's a lot of trade still done along this river. There's a lot of industry along that river. You've got a big port over there where stuff gets shipped up and down the river. And if the river was to start flowing this way, well, that cuts off all of that. And so that's why, even though the Mississippi wants to flow here, we artificially force it to continue flowing where it's flowing today. And that brings me to the random picture of the day. This is something called a broch. A broch was a farmstead. And these were built in the highlands and islands of Scotland around 100 BC to 100 AD. And they were usually a couple stories high. They are dry stone construction, which means there's no concrete, there's no mortar holding these stones together. They're just fitted together. And so there's a door, and basically a farming family would have lived inside there, 2,000 years ago.